Hello, welcome. Press. Well, choose. Well, read, think, choose, press. And I want to spend this time to point at this list, which I sent about 15 minutes ago to everyone. I also have a slide ahead. So don't read this list. It's in an email I sent. So this is just a reminder to everyone that out of 105 students still registered for this course, '21 students are absent so far, technically. So today, that's the only day when I'm going to pass around two sign-in sheets. This is standard one for your signature, and this is one you saw once before for your radio ID. So I'm doing my part. Preparing lectures, homework assignments, lab manuals. I'm not talking about the quality, but all features of the course are present. You should be doing your part. So 21 students still haven't done some parts of your part. All right? So I would expect number 5 would be most, because that's basically what it is. If you're not sure, that means picture is not clear. If picture would have been clear, you would know for sure. Well, nothing also is good, but there's one feature of this diagram which confused me. That's why I personally considered it as at least partially strange, weird, you know. That's the ground, and that has to be parallel to the ground. Not a big deal. It's just, again, to start a conversation. So I've composed a list of pictures which I consider missing some features or not clear in certain parts. And so another one. Well, it's a good exercise at home to browse and to make a statement. What do you think should be fixed to make it as clear as possible? You know, for example, the direction of acceleration, missing acceleration, direction of acceleration. But I also have a list of pictures which I personally couldn't find anything wrong with. Again, no names, I don't know which pictures whose, but these are nice. There was one, yeah, this is a part of the large picture which actually shows that banked track, and definitely the person used ruler, which is also kind of neat, yeah, if you compare all other pictures. Well, people would agree normally that doctors and teachers have very bad handwriting. I don't know what it's related to, but for a surgeon, for example, being manipulated with the hand as accurate as possible could have been a very, very good skill, you know, if you make a surgical cut. If it has to be straight, that kind of wouldn't work, right? So drawing pictures accurately, as accurate as possible, might seem kind of silly, but it's directly related to one of the important skills which some of you in the future might require. Moving on, that's my last call. You see, it's this is the last call. Physics. Any questions? Suggestions? Propositions? Ideas? Okay. So, a Carnival Ride, I wouldn't recommend anyone. It's scary. But basically, it's something like this. You walk inside, you stand on a, well, kind of seat, it spins, and eventually that seat goes down, and you're just floating. So the physics behind this device, experiment, fun stuff, is exactly what we're talking about right now. This sponge represents you, and of course, if I just let it slide, it slides down, no matter if it's inside or outside. If I spin it fast, what do you think is going to happen? It still slides. Well, forces acting on this sponge, of course, force of gravity. There is a normal force, and there is a force of friction in general. If it slides, that's kinetic friction. If it sticks relative to, it doesn't move relative to this wall, that's static friction. So basically what we want to do, we want to increase the static friction so it would have been strong enough to prevent it from sliding. We can do it differently. For example, put some water, make it wet. Why is it blue? What do you think? I added some dye, food coloring, that's it. Nothing special. So now it sticks. And it's going to stick until I slow it down to a certain speed, and finally it slides down. So let's just use this experiment to practice in analyzing circular motion with constant speed, which we call a uniform circular motion. Come on. So you should do, first, you should do your picture. And you don't know, will I ask you to send it to me or not? So try the best you can. You should draw a free body diagram for that sponge stuck to the wall. You can use a top view, or you can use a side view. Yeah. Of course, it has to be a snapshot, a photograph. The top view is what you would have seen from looking straight down. The side view is what you see, well, right now. It's a good practice exercise to draw both. If you look from the top, that's what you see. And this sponge. The force of gravity points away from us, so we kind of can't see it using this perspective. And the normal force points towards, well, it has to be perpendicular to the wall. So the normal force points toward the center of this circle. So the normal force is responsible for the centripetal acceleration. And another force of static friction, again, is invisible if we use the top view. So if we use the side view, we just see a wall, well, of this bucket. That's the sponge, the same normal force, and there's a force of gravity acting down, and that's the force of static friction. And the magnitude of the gravity should be equal to the magnitude of the static friction. And m times centripetal acceleration should be equal to the normal force. That's it. And the force of static friction is equal to the coefficient of static friction times the normal force. Now, if you agree with everything I have written right now, please raise your right hand. Well, raising doesn't mean this, raising means this. Okay, got it. Now, if you disagree, please raise your left hand and be prepared to tell me why, what's wrong. Yes? That's a good point, but they all absolute values automatically. That's a standard assumption. Only when I want to show very clearly, specifically, to avoid any ambiguity that I'm using absolute values, only then I use vertical bars. Otherwise, every variable automatically means absolute value. So if you want to, we can add them, but that's so now let's ask again. Now, if you agree with everything on the screen, please raise your right hand. You'll agree. If you disagree, left hand. What? I marked it. It's AC, centripetal acceleration. Good point. If anybody disagrees now, please raise your hand. Yes? Exactly. Thank you. We can't write that last equation. That's not how it works. The force of static friction is equal to whatever it equals to. All the maximum value of the static friction is equal to coefficient times normal. Thank you. So another missing element. So the force of static friction in general is less or equal to this. Well, now basically we're done. So m times v squared divided by the radius of this circle, which is this, right? Or this, has to be, well, in general, less or equal to the coefficient times what do I do? So normal force, actually, normal force. Let me rephrase this. So this come back. This is equal to the normal force. But in this situation, the normal force is supposed to be greater than or equal to the force of static friction divided by the coefficient. That's how we solve this inequality. So, which is saying, same as saying it should be greater or equal to mg divided by the coefficient. So that should be greater than or equal to mg divided by the coefficient. Only when this condition, sustained, fulfilled, works, only then the object doesn't slide down. So we can cancel masses and basically solve it. The coefficient times speed divided by the radius times gravity should be this. So there is a critical speed, for example, for a combination of other variables. The speed should be greater than square root of rg over mu. If it's greater, that's it. Force of static friction is sufficient to prevent it from sliding down. But if it's getting slower and slower and slower, eventually the speed goes below the critical value. The force of static friction is not sufficient anymore to prevent it from sliding, and it slides down. Any questions? So now let's do a couple more examples related to the vertical motion. We saw this slide. Yeah, we just said that if you have any object, like a ball on a string, for example, making a circular motion, we can easily analyze two specific situations: the highest point, the lowest point. That's what we did. And for different cases, the centripetal acceleration might be related to the different force. If it is a car traveling through a loop, that's a normal force. If it's a ball on a string, that's a force of tension. So the nature of the force, again, doesn't matter. All we have to do is just to write equations, and we did, and solve them for wherever we need to solve it for. So you can start thinking about this case. This is a plastic bucket on a string, so I can make it move in a circle. And note just the vertical circular motion sometimes can be uniform with a constant speed, and sometimes can't. For example, if you have a ball on a string, speed changes. So that's not a uniform circular motion. It's slowing down, speeding up, slowing down, speeding up, slowing down, speeding up. But still, even for this situation, two extreme situations, the highest point, the lowest point, is very easy to analyze. If you have, for example, a stuntman on a bike, on a motorcycle, in that case, that person can maintain the constant speed, just by speeding up or slowing down the motorcycle. So in that case, we can apply exactly the same reasoning to any location of that object, because speed is the same everywhere. Well, just a note. So what's going to happen? Well, nothing if I'm fast enough, right? If I move it relatively slowly, at some point, it falls out. Of course, when it's a ball, it's not really scary. It's much scarier if instead of the ball, you have a water in it, right? So you guys now in a splash zone. Well, the last time I did this experiment was about half a year ago. Who knows how it might go now? Well, of course, I'm not going to reach the critical speed. It's not a ball. Who would clean it up? But you get the gist. If I had to move slower and slower, eventually, like a ball, this water would fall out. So this is what the question is about. What's that critical speed? If I spin it fast enough, above that critical speed, everything's fine. But if I slow it down below, that's it. Well, that's what the question is about. Well, which of these two diagrams should we use? On the left or on the right? On the right, exactly, because it is related to the top, the highest point of the trajectory. So we just have to copy the diagram. Well, there is normal force acting from the bottom of this bucket on wherever it is. Could have been water, could have been a ball, doesn't matter. That's the normal force. And again, at that particular instant, the acceleration points straight down, and the force of gravity, mg, also acting straight down. So we can stick to our choice of positive y direction upward and write using magnitudes. When we spin it fast enough, the normal force, well, is not zero. What is happening to the normal force when we make it move slower and slower and slower? Well, the normal force decreases in magnitude. What the smallest amount, what the smallest magnitude the normal force might have? What is the smallest magnitude for the normal force it might have? 0. That's the smallest number for any magnitude. Magnitude can't be negative. So that's the condition for the critical speed. So, well, first of all, we can multiply everything by -1. So plus, plus, plus. Now, mv squared over r critical is being reached when normal force reaches 0. And that tells us, again, m cancels. That tells us how to calculate that critical speed. Depends on the radius. It depends on the acceleration due to gravity. If you spin faster than this, everything's fine. Everything stays inside. But if you reach this and that's it, just a little bit slower, and it's going to fall down. Questions? There is another situation similar to one of your homework problems, which is directly related to the same calculation we just have done. Instead of a car, now I have a ball. That's why I placed it here. I knew the exact trajectory. So if it starts running down from this particular height, it reaches this particular speed. And as we know, there is a critical value. So if it doesn't move fast enough, it actually might even take off before reaching the highest point. But if I start moving from a very reasonable height, come on, it's getting through. So of course, between this situation and this situation, there is that critical height when it gets through, barely. What does barely mean? We have to make a mathematical statement about something. If you have to solve a problem about something critical, you have to formulate mathematically a condition for something critical. So this height will be critical when something is equal to something. That's what we have to write down. So the condition for the critical height is something, should be equal to something. So please give me some suggestions for some things. Anyone? Not enough? Enough. So what should be equal to what? Yes? How do you know? That's what we're looking for. We are looking for the height. So basically, you're saying the height's supposed to be equal to the diameter. We don't know. Until we have it solved, h equals to something, we don't know the answer. The word is critical. Should consume all your attention right now. How do we state the condition for something to be critical? We did it in a previous problem. Critical speed, we said, is reached when the normal force at the top becomes equal to 0. So the normal force is equal to 0 in the previous problem. That was the statement for the critical speed. So we should write some kind of a statement in this problem. Any suggestions? Well, now you have to say something. Well, what's the difference between a ball touching the rail and water touching the bottom of the bucket? No difference. If there is no difference, what does it mean? Same equation, same condition. Again, when the ball easily traveling through, it touching the loop everywhere, so there is normal force acting on it everywhere. If it doesn't reach the top point, it means there is no normal force. The critical situation, when it still travels through, barely touching this. So the critical situation is when the normal force here becomes equal to 0. That's exactly same condition. If it's exactly same condition, that's exactly the same problem, the exactly same solution, the exactly same answer. For what? For speed. Yeah. We can write immediately that critical speed here at point C has to be equal to square root of the radius of the circle times g. Any questions on that? Same acceleration, same normal force, same force of gravity, same condition, same calculation, same answer. It's just speed is not what we're looking for. Yeah? We are looking for that initial height. So now we have to relate this speed at point C. And this letter C has two meanings, point C and critical. And the initial speed, the initial height, it's being released from height, speed. Any suggestions, please? What law can we use to relate these two quantities? Height, speed. Yes? That's not the law. That's the name of one of the energies. But that energy might be a part of some law. So what is the name of the law which involves energies? Well, now I hear parts of that name, so I want someone to say the complete name. Exactly. Thank you. The law of conservation of mechanical energy, we said it. So by saying that, we excited a certain part of our memory, and now we can write the law. So this speed has to be equal to this. Well, the positive y direction is up. The origin is here. It's been chosen for us. So final height for this particular process equals a diameter, 2 r's. Now, we release it from rest. That's another meaning of critical. If we actually tossed it, we could do it from any height, even from the bottom. So now, the initial speed is 0. The initial height, that's what we're looking for. The final speed is square root of rg, and the final height is this. Mass cancels again, and you can solve it. So y initial will be equal to r over 2 plus 2 r, so 2.5 r's. G also cancels. So see, that's not a diameter. That's a diameter and a half of a radius. Now, just again, keep in mind the experiment which I did is not exactly what this problem is about, because in my experiment this ball also rolls. So that's one of the future topics. And this motion also has some extra energy. So what we're solving for is like a piece of ice, very slippery, sliding down. Just sliding down and getting through. And now we have to start talk about circular motion when speed changes. To illustrate how can it happen, I've got a simple demonstration. That's not a ball on a string. It's not rolling. It's just well, like a puck and nut. And well, there's force of friction acting on it. So I can still move it circularly. But the experiment I want to discuss looks like this. I give it initial speed, and then it stops. That's it. So after I pushed it, there's force of gravity acting on it, normal force, force of tension, and what else? What does make it stop? Friction. So, and of course now, initial velocity, well, initial speed, velocity always changes with circular motion, but initial speed was not 0, final speed is 0. Speed also changes. So the question is, how can we describe this situation? So we start from a free body diagram. I gave it a push. It was traveling, well, we call it clockwise, right? And because of the friction, it stops eventually. The centripetal acceleration stays, doesn't go anywhere. Still, there is circular motion, and still there is speed, which related to angular speed. Exactly the same equation. Again, nothing new so far. But now, because speed changes because of the friction, the total acceleration must have two components. In addition to the centripetal acceleration due to tension, it also should have an acceleration due to friction. That acceleration has a name. It points tangent to the trajectory, like velocity. So that's why we call it a tangential acceleration. And the total acceleration, of course, now should have magnitude equal to, well, that Pythagorean theorem. So this arrow represents the direction of the net force. This arrow represents the direction of actual acceleration. But still, you always can resolve it into two components. One component points toward the center, the normal one, v squared over r, nothing new. But the new component now should be related to what? Well, if speed changes, angular speed changes as well. So this acceleration, tangential acceleration, should be equal to change in speed over time. And if angular speed changes angular speed over time, that's what we call angular acceleration. For a uniform circular motion, angular acceleration equals 0 because angular speed, angular velocity doesn't change. But now it changes. So this slide describes all old and new connections. This is same centripetal acceleration. This is Newton's law, two components written. One relates centripetal acceleration and force of tension. Second relates new tangential acceleration and force of friction. This is an official definition of the tangential acceleration. Well, strictly speaking, we should say the average acceleration, but we can ignore it in most cases. So final speed minus initial speed divided by time. This is what we call now angular acceleration. If angular velocity, angular speed, we use those terms with the same meaning, here in this course. So if omega changes, angular acceleration is not 0. If omega doesn't change, angular acceleration is 0. If angular acceleration is not 0, well, this is how we can relate the angular acceleration and tangential acceleration. See, very similar relationship. Linear speed, angular speed, linear kind of acceleration, angular acceleration. This is what we have to keep in mind. For any circular motion, centripetal acceleration is never 0. But tangential or angular, it depends. If it's a uniform circular motion, if the speed doesn't change, 0. If speed changes, not 0. And this slide helps us to see analogies and memorize equations if we want to. These equations we used to use for linear motion with constant acceleration. the velocity equation, the motion equation, the third equation, which has no name, which is the name of this equation. And same here. The velocity equation, just angular velocity. The motion equation, position equation, just angular position, angle. And that third equation, which has no name. Absolutely similar equations. Now, remember the slide with 4 pictures of car and equations related to direction of velocity and acceleration. We know when an object travels to the right and speeding up, acceleration points to the right. But if an object travels to the right and slowing down, the acceleration points to the left. Because when objects speeding up, acceleration and velocity are parallel. When an object is slowing down, acceleration and velocity are opposite. Here, when we talk about rotational motion, circular motion, we don't call directions usually left and right. We call them counterclockwise and clockwise. That's how we call them. So for example, this picture shows a counterclockwise motion. What does it mean? Well, angular velocity, we say, directed counterclockwise. What does it tell us about angular acceleration? Angular velocity is counterclockwise. That definitely means angular acceleration is also counterclockwise. Yes or no? No. We also have to say what's happening to it. If it's speeding up, if it moves faster and faster, in that case, angular acceleration also will be counterclockwise. Otherwise, will be opposite. Now, when we talk about linear motion, we use x and y axes, x, y. Here, when we talk about rotational motion, well, this is kind of top view. We use different names. If this happening counterclockwise, we also call it out of the screen. That basically represents the third axis, z, x, y, z in general. So the language, we just need to know the language because you may read the problem and you need to know what it means. If it says velocity, angular velocity points out of the screen means counterclockwise motion. That's it. That's just the language. That's our agreement. Remember, in the past, all angles measured counterclockwise, we called positive. But angles measured clockwise, we called negative. And, well, this is what people do in physics. If you want to figure out or in, you just look at your fingers, which curved in the direction of the, well, whatever it says, counterclockwise, the thumb points out of the screen. We say it towards us. For the clockwise direction, same rule. The thumb points into the screen, we say it away from us, or we say it into the screen. We're going to use this language in the future sometimes to clearly describe what's happening. So we should understand. That's our dictionary. Yes? If you do in a side view, that's a top view, right? So if you do in a side view, you have 2 options. Number 1, you have to go behind the screen and look at this like that. What would you see? What would you see? That's where the imagination again becomes handy. That's the top view. What do you see the whole circle. What do you see now? Just the side. The picture actually for the side view looked like this. Because that's what you see, just the rim. Imagine that's a ring, and that's only what you see. But now imagine what is, so here, we have to imagine an arrow pointing away from you. So now, in your mind, you're turning this around. What's happening to that arrow? Down. So for the side view situation, this arrow will be visible, but you will not see the circle. So it's a trade-off. You want to see the circle, okay, you do the top view, but you cannot see that arrow. So you just have to use a representation. This cross means away from you, like an actual arrow, you know, you shoot from a bow. And this dot means towards you. That's what you see when arrow flies at you, and, well, whatever happens, happens. So this is an example of a situation where we may need to manipulate with objects, three-dimensional objects, you know, mentally. That's what you see. In your mind, you can turn it like this, or you can turn it like that. We should imagine this arrow kind of glued up to this circle, right? Imagine. So that's what you're imagining, this arrow. If you make a turn, it turns with this. It remains perpendicular to the circle. Again, that's just a language, but that's an important part of our conversation. We need to know that language. Questions? We're done with circular motion, kind of in general. So the next topic is gravity. So any questions about circular motion? All right. So this is the law, the fourth law, given to us by Sir Isaac Newton as a gift to mankind. So if we have two objects, they attract each other. And this is the magnitude of the force between two objects. It's a mystery how he could have guessed it. But he did, and it works. So the conditions when this law can be used are, number one, those objects supposed to be spheres, and a point, a dot, is also a sphere which just has no radius, no size. So it also includes points. Second condition, which in all our problems always presented, the density is uniform, you know. So it's like a planet with a uniform density inside. In real life, that's not the case. The core, for example, the Earth core is very dense. So we neglect all this difference. And this is just a fixed number. Newton didn't know the value of this constant. It's been measured later by Sir Cavendish. And this is just a fixed number, the gravitational constant. Newton meter squared, kilogram squared. You see the number is very, very small. So force of gravity is actually very, very weak. To make it strong enough, we need a huge amount of matter, planets, stars. And if we have two huge objects, two very heavy, so that's going to be the mass of the first one, that's going to be the mass of the second one, And that's going to be the distance between the center of the first one and the center of the second one. All right. Thank you very much. We're going to pick up from this slide on Friday. Take, oops, these two, thanks. And please don't forget 2 sign-in sheets floating around.
My number was one of those on the board, but I think I've only missed one.
It doesn't matter if your number is on the board, you have to do what the board tells you to do.
Okay, so I'll send you an email.
Yes.
President, I had a quick question.
Yes.
I can't make it to my discussion on Friday. Do I have to, like, can I just show up to another one? I can't
Yes,
make it to the,
you
I don't
can.
have, do I have to sign anything, or I can just show up?
You have to choose which discussion you want to get into.
Okay.
And you should introduce yourself to TF, explain the situation, tell them that I said fine, it's a one-time deal,
Okay.
and it should be fine.
Okay, thank you.
I have a quick question. I misplaced my clicker. If I were to get a new one, should I just re-register it, or should I like email you the new number? Or?
You should send me. Well, don't buy a new one.
Oh no, I mean I have another one.
Oh, you have another one.
I have another one, but I'm still gonna look for the old one.
Okay.
If I can't find it, what should I do with the?
Send me an email.
Okay.
You're from now on you're using the new clicker. The clicker is this.
The reference ID you give me.
Yeah. You don't need to go to registration.
Okay. Thank you.
I'll take this one.
Jason
They were there. I'm still waiting for them.
Oh.